Hey Wheaton North, we're going to talk about the law of conservation of mass today. Before I get started and talk through some things, we're going to watch this quick video.
The atoms that are the fabric of all things. To answer that question, we look to the law of conservation of mass. This law says, take an isolated system defined by a boundary that matter and energy cannot cross. Inside this system, mass, aka matter and energy, can neither be created nor destroyed. The universe, to the best of our knowledge, is an isolated system. But before we get to that, let's look at a much smaller and simpler one. Here we have 6 carbon atoms, 12 hydrogen atoms, and 18 oxygen atoms. With a little energy, our molecules can really get moving. These atoms can bond together to form familiar molecules. Here's water, and here's carbon dioxide. We can't create or destroy mass. We're stuck with what we've got. So what can we do? They have a mind of their own. Let's see. They've formed more carbon dioxide and water, 6 of each. Add a little energy, and we can get them to reshuffle themselves to a simple sugar, and some oxygen gas. Our atoms are all accounted for, 6 carbon, 12 hydrogen, and 18 oxygen. The energy we applied is now stored in the bonds between atoms. We can re-release that energy by breaking that sugar back into water and carbon dioxide, and still, same atoms. Let's put a few of our atoms aside and try something a little more explosive. This here is methane, most commonly associated with cow flatulence, but also used for rocket fuel. If we add some oxygen and a little bit of energy, like you might get from a lit match, it combusts into carbon dioxide, water, and even more energy. Notice, our methane started with 4 hydrogen, and at the end, we still have 4 hydrogen, captured in 2 water molecules. For a grand finale, here's propane, another combustible gas. We add oxygen, light it up, and boom, more water and carbon dioxide. This time we get 3 CO2s, because the propane molecule started with 3 carbon atoms, and they have nowhere else to go. There are many other reactions we can model with this small set of atoms, and the law of conservation of mass always holds true. Whatever matter and energy go into a chemical reaction are present and accounted for when it's complete.
Alright, so to recap, and what you should have in your notes under law of conservation of mass, is the really simple idea that however many reactant atoms you start with and what they weigh, their mass, has to be accounted for at the end. You can't lose any. Whatever starts in your system with your reactants, you have to have as your products. The elements are just rearranging like they showed in that video. Alright, just to show this one more time, this is the same demo I'm going to do for you that Mr. Yergler just did in Notes 1. I have the same 2 reactants that he started with, and you can see that they have a mass of 101.3. And when I pour them into each other, you get that awesome color change. So you're getting a brand new precipitate, 101.31. So our mass of our 2 reactants when they were separate is exactly the same as our mass of our product. Here's one more picture of another reaction. This is 2 clear and colorless solutions reacting. This time they put a lid on the top to just prove that it's a closed system. I didn't have to do that with my demo, and Mr. Yergler didn't have to either, because those are both liquids and they're both solids, and they both, like settle down to the bottom. If our reaction that we chose made a gas, it would have been really important to have a lid on the top to keep all of those atoms in the system that we had. So really quickly, I'm just going to go through a few more examples of law of conservation of mass, and Mr. Yergler is going to go into this with our next video on balancing. When you have atoms before, we call them reactants, and afterwards they have to be the same thing. Here, I'll show this over here. So if you start with 16 X atoms, they have to be there at the end. Your 8 Y atoms have to be there. You can see that they're rearranged, but they're all accounted for. We have some vocabulary and some ideas and some particle pictures that you need to kind of be familiar with. Take a moment to pause the video and read through this, but the big idea is that subscripts, this number down here, tells you how many atoms are in one molecule. So CO2, one molecule, has 2 oxygens and 1 carbon. A coefficient is this number out front. This tells me that I have 3 molecules. Both important words and vocabulary things to understand the difference between those two. Some other vocabulary that will really help you out in this unit. Before the arrow, you have your reactants. Those were the 2 clear and colorless beakers that we started with. And then your yield sign is showing that you are reacting these things and rearranging all of the atoms. Your products are what they turn into. So that would have been the yellow precipitate that we made. The coefficient tells you how many compounds or molecules. The phases we'll get into later too will tell you, G is a gas, S is a solid, L is a liquid. We'll have one called AQ, aqueous, which means it's a dissolved solid. So we're going to include all of those in our reactions as we go through this unit. All right. Reactants, this is a new reaction, iron and chlorine. So we have solid iron and chlorine gas. How many are reacting? When you look at 3 Cl2s are reacting, to figure out how many chlorines are reacting, you can draw it out like we've been showing in all these pictures, but that takes a lot of time and you're going to want to do your homework a lot faster than that. We're going to make you draw some of these out, but not all of them. So to do really quick math in your head, take your coefficient times your subscript, and that will tell you how many atoms are reacting. Oh, it says 6 there. And just yet one more. The 2 irons that you start with are accounted for. The 6 chlorines are accounted for. So these coefficients are going to tell us how many of each molecule we need, so we're not losing any atoms. All right. Another really important concept, they talked about it in the very first video. A system is what you're studying. The law of conservation of mass lab that you did or will do, you're working with 2 different types of system, an open system and a closed system. A closed system will keep any gases locked into your system and won't let them escape. An open system, the gas can escape and water vapor and air can move through it. Both of them allow heat transfer. If you truly want a closed, isolated system with even no energy going through, you need an isolated system. So you'd have to have some sort of insulation around the outside. We're going to work with an isolated system second semester. But an open system is going to affect your ability sometimes, especially if you are working with a gas.
We made it. Can you imagine the look on McGonagall face if we were late? That was bloody brilliant.
Thank you for that assessment, Mr. Weasley.
Movies are notorious for messing up the idea of conservation of mass. If you can find another example in a video clip and post it to the classroom assignment, I'll give you a little extra credit. Make sure that your video that you're picking is unique and nobody else has already found that. So take a look at what other people have done, if they've done it. All right, so that's the law of conservation of mass. Mr. Yergler is going to talk to you next about balancing and how to figure out how many compounds of each reactant and product you're going to end up with, and still accounting for the same number of atoms before versus after, no matter how they've rearranged.